Good afternoon and welcome to Check Stoichiometry live office hours. It is so great to have you. If this is your first time, welcome. We'll be running this session. I'll start with some warm-up problems, and then throughout this session, I encourage you to ask any questions that you have. If you're coming back from another live stream or you've been on this live stream before, it is so great to have you. Thank you for joining us again, and thank you to Chegg for putting these live office hours together so that we can all learn more about the topics we are focusing on in college. I'm Allison. I'm your instructor for the Stoichiometry Office Hours. I have been a TA in regular chemistry and then entry-level organic chemistry and nursing chemistry. I've also been a student learning assistant for nursing chemistry. And then I have also done some tutoring in calculus, but I love chemistry and I would love to teach you. I've prepared some questions to start, but again, throughout the live stream, I'm here to help you. I'm your resource to learn. So I encourage you, anything you have a question on, if you want clarification, ask it. If you have a homework question or something you went over in class that you want help on, ask that. You can type it in the chat of wherever you're streaming from. So TikTok or YouTube, you can type that. And I also encourage you to try to beat me to these answers. That way that you're really checking the work and making sure you know how to do the problems I'm giving. So if you want to try to beat me in the chat to answering the question, I really encourage you to do that. And I'm going to ask some questions throughout this live stream that I want you to try to answer, maybe conceptual. That way we can understand chemistry as a whole. But let's get started doing some stoichiometry. It is so great to have all of you. So I wanted to start with a few warm-up problems. The first being convert 746,538 milligrams to kilograms. If you're new here, I like to use what's called the factor label method when solving stoichiometry problems. This is like a true stoichiometry problem in my opinion. It's getting one thing to another, and it's a straightforward type of math. I use the factor label method because it helps me visualize and helps me put it in my calculator easily. But basically, to do this, we're going to start by writing what we're given. And in this problem, we are given 746,538 milligrams to start. And I got that from right here. So again, I encourage you, beat me to solving this problem. Especially if you're coming back from other live streams that you've had that I've taught, beat me in solving this problem. All right. Then what I want to do is I want to go to something that I know. I want to convert to something that's going to get me closer to kilograms. I don't know the conversion from milligrams to kilograms off the top of my head, but we have these things called base units. So your base units are grams, liters, there's other ones. I can't think of them right now. But those base units, everything is in reference to that base unit. So we can easily do 2 grams. That would be the first place I would start. And I put milligrams on the bottom because whatever's on the top, this is like a math rule. Whatever's on the top, if I want to cancel it out, I want to cancel milligrams out since milligrams isn't my final answer. Whatever's on the top, I put on the bottom and I can cancel both out. Now I'm at grams, and we can go ahead and put that conversion factor in. If you know the conversion from grams to milligrams, I encourage you put that in the chat. I'm going to give y'all about 10 seconds. Give me that conversion. Let's see how much y'all have memorized. My teacher made me memorize this, so let's see how much we're learning in our chemistry classes. All right, 3, 2, 1. If you said 1 gram is 1,000 milligrams, you're absolutely correct. Great job, guys. And then we're going to go one step closer to kilograms, which in this case, since we're already at our base unit, we can go straight to kilograms. So we put grams on the bottom because, again, grams isn't in our final answer, so we want to cancel it out. But kilograms is in our final answer, so it goes on the top. So then we cancel our grams out because it's on the top and the bottom. And now we need a conversion factor from grams to kilograms. So I'm going to give y'all another 10 seconds. Tell me that conversion factor from grams to kilograms. I think memorizing these is extremely important. So I want to test y'all and make sure that everyone is understanding. All right. If you said 1 kilogram has 1,000 grams, you are absolutely correct. Now, the reason I like this factor label method is you're probably wondering, hey, we've just like put a bunch of random numbers and some symbols on this little sheet. What are we going to do now? So the way the factor label method works is you multiply everything on the top and you divide it by everything on the bottom. So I can kind of put my division thing on the bottom. John and Andrew, y'all did great. 1,000 grams and 1 kilogram is absolutely correct. So great job, guys. And so let's put this in our calculator. I'm going to show you, I'm going to write out exactly what I'm going to put in. I'm going to put 746,538 divided by 1,000 times 1,000. I'm going to give y'all 30 seconds. Put this in your calculator. Beat me to getting that answer, okay? So y'all have got about 30 seconds. All right, we've got about 15 more seconds. See if you can beat me. I believe in you guys. All right, 5, 4, 3, 2, 1. If you said 0.7465, you are absolutely correct. If we wanted to do sig figs correctly, we would just add a 3/8 into at the end. But that's going to be our final answer. And that unit, we always want to include our units. That unit is kilograms. If you're a little confused on the sig figs, stick with me. We're going to do some more sig fig work here in a minute. And then sig figs, if you're wondering what that means, because I sometimes speak in chemistry lingo, that is significant figures. That's what my high school chem teacher called it. And now I cannot get that out of my head. So it's significant figures. You might have heard your chem teacher talk about that. But that's our answer. If you have any questions on how I got there, type that in the chat. I'd be more than happy to explain it better if we need that. And if you're just now joining, welcome in. It is so great to have you. I'm Allison. I'm your host for Cheg's live stoichiometry office hours. I encourage you throughout this session, ask whatever questions you have. You can ask homework questions, things you went over in class, conceptual questions, anything about chemistry. We have a comment from Gorge on TikTok. Could you help with acid-base equilibrium? Absolutely. If you type one of those questions in the chat, I would be more than happy to help with some acid-base equilibrium. That is what I'm here for. I want to answer any questions y'all have. While we wait on some to roll in, we're going to go to our next warm-up question just to get y'all in that chemistry mood. It's balancing the equation C4H8 plus oxygen. Now, I wanted to kind of trick y'all up with this because we've had lots of practice balancing equations. Hopefully most Chem 1 and Chem 2 classes have by now. So I want to see if you all can figure out what the products of this reaction are going to be. So I'm going to give y'all 15 seconds. Tell me what the products of this reaction are going to be. I do see a comment from John on TikTok about maybe going over some sig fig stuff. After this problem, we will jump right into some sig fig questions. So stick with me, and I promise I will explain all the zeros and dots and stuff about sig figs. All right, you've got about 10 more seconds. Tell me, what are the products of this equation? This is a combustion reaction, if that helps you guys. I know some classes learn it by type of reaction. This is a combustion reaction. All right, if you said yield CO2 plus H2O, you're absolutely correct. All of our carbon combustions always yield carbon dioxide and water. So now we need to balance it. If you've been in some of my past sessions, what I will say is start with carbons. It's always easiest to start with carbons, and it's always easiest to end with oxygens. So I see I have 4 carbons over here, so I'm going to put 4 carbons over here. I have 8 hydrogens over here, so I'm going to make 8 hydrogens over here. The reason I put a 4 as my coefficient is because 4 times 2 equals 8 hydrogens. So that equals out my hydrogens. And then I count how many O's do I have on the right side, and I make it equal the left. So I have 4 times 2 O's over here, so 8. And then I have 4 oxygens over here, So if I add those together, I get 12 oxygens. If you need me to slow any of this down, let me know. I kind of just wanted us to do some fast, like little warm-up problems. So if I have 12 oxygens on the right, I need 12 oxygens on the left. So I would do 6 as my coefficient because 6 times 2 equals 12. And then I want to do one last little final check to make sure everything on the left equals everything on the right because I'm human and I can make mistakes. I always recommend this if you're taking a chem test. So we have 4 carbons over here, 4 carbons over here, 8 hydrogens over here, 8 hydrogens over here, 12 oxygens. 8 plus 4 oxygens is 12. That is our balanced equation. Send a thumbs up in the chat if you're kind of understanding where we're going. Now, John from YouTube, I am going to work on some sig fig stuff. So this is really important. It's on lots of people's finals. So if your finals are coming up or maybe some midterms, I encourage you to listen in. We're going to be working on sig figs. So, and then I do see a comment from Aqua Shark on TikTok. Can you go over gas laws? Absolutely. I would love to do that. Any questions you have about gas laws, type those if there's something specific. I don't have anything prepared right now, but I can probably come up with something. But I would recommend if you have a gas laws problem, type that in the chat. I would love to answer that for you. Okay, so now we're going to do sig figs. So we want to know how many sig figs are in each of these. So first, we're going to start with A. We have 7.489 times 10 to the 27. This is a kind of easier sig fig one. Our first rule of thumb is all non-zero numbers are significant. I'm going to abbreviate significant as sig. And I'm also going to add another kind of little rule. All zeros between non-zero numbers. So your non-zero numbers are 1, 2, 3, 4. And 5, 6, so on. Between non-zeros are significant. So those are our first 2 rules. Now, knowing these 2 rules, how many sig figs would we say is in 7.489 times 10 to the 27th? So I'm going to give y'all about 20 seconds. If this is something you're struggling on, this is a great question and something that you really need to know. So great job for asking these questions, but I also encourage you to participate. So if you know how many sig figs are in this first one, you've got 10 seconds to type it in the chat. We'll check everyone's learning and see if everyone is kind of understanding. All right, we've got about 5 more seconds. How many sig figs are in 7.489 times 10 to the 27th? All right, if you said 4, you are absolutely correct. I'm going to show you all how I got that. So our rules, all non-zero numbers are significant and all zeros between non-zeros are significant. So in this problem, we only have 4 non-zero numbers because this 10 to the 27th is just a bunch of zeros. And we have no zeros between those non-zero numbers. So we have 1, 2, 3, 4. Send a thumbs up in the chat if you're understanding how I got that 4. That one was kind of an easier one to start with. But now this next one is a little bit more complicated. So I'm going to give y'all 10 seconds. Tell me how many sig figs you think are in this problem. Then I'm going to give you a new rule about significant figures. And then I'm going to give y'all some more time to see if you want to readjust your answer. But 10 seconds, type an answer in the chat. How many significant figures are in B? This 0.000 and so on number. All right, so now the rule that we're going to get is if there's a decimal point, you want to go from left to right, and the first non-zero number you hit equals your first significant number. And then you count, you keep going left, and when you hit no more non-zero numbers, you stop. I know that one's a little bit harder to write out, but if there's a really small number, really small decimal point, you start, go to your first non-zero number, and I'm going to show this in a minute, and then you stop, count how many significant figures you have, and when you are out of non-zero numbers. All right, so if you want to readjust your answer, you've got about 10 more seconds. I see some comments for 13. I see some comments for 7. Let's see if we can reach a consensus. All right, so this is how I would solve this problem. I'd start at my decimal point and I'd cross out these zeros because according to my rule, if I'm starting at the decimal point, all of those zeros until I get to the first non-zero number don't matter. Then I have a non-zero number here, 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 here. Then according to my rule number 2, all zeros between non-zero numbers are significant. So I have two zeros here that are significant, and then I have another non-zero, so that's significant. But then after there's no more non-zero numbers left, everything after that is not significant. So if I count how many sig figs I have, I should get 7. So John from YouTube, great job. 7 is absolutely correct. Then our last significant figure kind of question is how many significant figures are in 110,000? So I'm going to give y'all about 20 seconds to answer this. If you have no decimal point, this is the rule for that. No decimal point, you start at the right and you go left, and the first non-zero number is your first significant figure. You go till you hit no more non-zeros. So 20 seconds, tell me how many sig figs are in 110,000. And then if you want any more practice with sig figs, let me know in those comments. You've got 20 seconds. All right, about 10 more seconds, guys. How many significant figures are in 110,000? All right. If you said 2, so I see a 2 from Century on TikTok. You are absolutely correct. 2 is great. So we would start at the right and we'd go left. We count out all of these because they're zeros, but then we hit a non-zero here and here. So that would give us 2. And so hopefully that makes more sense as far as sig figs. If you still have questions, let me know in the chat and can go over more. We did get a question from Aqua Shark on TikTok. What are the relationships between volume, temperature, and pressure of gas? So your go-to equation for gas laws is going to be PV equals nRT. If you haven't heard of this yet, you will. It's coming. It's a great question. But what we need to do is, this is kind of a more conceptual question, so we're going to conceptually work through this. What is the relationship between pressure, volume, and temperature, I think? Yes. All right. So here's how I like to think of it. I like to set a number as one side of the equation. So I'm going to set my number as 10. And I'm going to first focus on the relationship between pressure and volume to kind of show this. If my pressure is 1, my volume is 10. Now, let's say I increase my pressure. So let's say I move my pressure up to 4. And if you need units, we can do 4 ATMs. And we've got 10 ATMs on the right side. Now, if and this will be liters, so ATM liters. And then if I have 4 as my pressure, to get that 10 still on the right, I'm going to have to make volume 2.5. So looking at just this kind of example, as pressure increases, so that up arrow means increases, my volume decreases. And so I can just see this as my pressure went from 1 to 4, my volume had to go from 10 to 2.5 to equal that 10 on the right. Is that kind of making sense? So as pressure increases, volume decreases. So that's our first relationship. Now we want to do our relationships to pressure and temperature and volume and temperature. So the way that I would look at this is, let's set pressure as 1, and then we just have volume, and let's set our N and R as 1, and we have T. So if I want my left to equal my right, if I made volume 1, temperature would have to be 1. But if I made my volume, let's say 12, my temperature has to be 12. So they're increasing together. So that's my first relationship. My second relationship is as volume increases, temperature increases. Another way we could write this is volume and temperature have a positive correlation. So they increase and decrease together. And pressure and volume have a negative one, if that helps. And then also, since our volume and pressure are on the same side of the equation, we could just kind of plug that in for P and see that pressure and temperature would have the same impact. So as pressure increases, temperature increases. Hopefully that answers your question, Aqua Shark. If you have any more questions, type them in the chat. But that's kind of the relationship between pressure, volume, and temperature in gas laws. Hopefully that helps. If anyone has any other gas law questions, I encourage you, ask those in the chat. I would be more than happy to help. I see a question from Parv Salo on TikTok, how to find molecular formula from given percent values of elements. I don't have an example on me right now, but if you have one, please type that in the chat because I'd be more than happy to go over this. I can definitely get one next week, but I would be happy to work on it this session. If you can type that question, some specific question with percents in the chat, we will work on that. All right, guys. So hopefully everyone is kind of understanding what we're learning. If you're just now joining, this is Chegg Stoichiometry Live Office Hours. It is so great to have you. I'm Allison. I am your host for tonight. I encourage you throughout this live stream, ask any questions that you have. I would be more than happy to answer them. I want everyone to leave this live stream having a better understanding of chemistry. So now our last warm-up question of the night is, we want to find the molar mass of acetic acid, which is HC2H3O2. I'm going to give y'all 1 minute to find this molar mass. Try to beat me to finding it. In about 30 seconds, I'm going to start solving it on the whiteboard so we can kind of move through and get to some other questions, but see if you guys can beat me in solving this. All right, you've got about 1 minute. All right, I would start by dividing my different elements in the compound. So if you can solve this on your own, keep solving on your own. If you're stuck and need help, look up on the board, and I'm going to start solving. I'm then going to go to the periodic table and find those individual molar masses for each element. So I have 4 hydrogens, and then this is moles. And then my molar mass on the periodic table is grams per moles, 1.01. So I cancel those out. You get 4.04 grams. Then for carbons, I have 2 moles of carbon. I have 12.01 grams per mole if I look at that periodic table. So I get 24.02 grams. For oxygens, I have 2 moles times 16 grams per mole. Those moles cancel out again. They did up here too. So I should have 32 grams. And then I'm going to add them all together as that last step to find the molar mass of acetic acid. So I add 4.04 plus 24.02 plus 32. I get 60.06 grams. If you got that, great job. And remember, type those answers in the chat to check and lock it in. But that is how we find the molar mass of acetic acid. And that is all of our warm-up problems for the day. So again, if you have any of those questions, if we do have a question on how to find molecular formula from given percent values of elements, type any questions you have in the chat. I would love to answer them, but for now, until we have some questions, we are going to work on a new skill, and that is electron configurations. We had a few questions on this last week, so I wanted to do a better job of explaining that and what an electron configuration even is. I know when I TA'd and tutored in chemistry, it was a really tough concept for students to grasp, and it's very conceptual and not a lot of practical application, but it's going to be on those finals, on those midterms, on those tests, so it's very important to learn. So hopefully this kind of overview will help you. If you need better clarification on anything I go over, type that in the chat and I can go through it slower, I can go through it more precisely, just let me know. But first, we want to know what the electron configuration of carbon is. So we have carbon, which is right here on the periodic table. It's C, is its abbreviation. Now, what we do is I'm going to kind of run through this first by basically labeling the periodic table, so it's going to help us. We're going to say this is our S. This right here is our D. This is our P. This is our F. So you're probably like, what does that even mean? It's going to come in handy. An electron configuration is basically a way to tell where something is on the periodic table by its electrons. And in electrons, we have S, P, D, and F orbitals. They all have unique shapes. And in each orbital, there are different subshells. S has one subshell, P has 3, D has 5, and F has 7. And in each of those subshells is 2 electrons. Now, that's more conceptual. There's a chemistry live office hour, so they could probably do a better job of talking about those specific orbitals, but I want to focus on the math and kind of the drawings behind it. So we are going to find how would we find carbon on the periodic table by doing this electron configuration. So we always start with 1s. 1s entails the hydrogen and helium. Hydrogen and helium. And since there's 2 electrons in the 1s orbital, we would put 1s2. And that 2 signifies 2 electrons. The 1 signifies the first orbital. And you could think, oh, it's the first row. If only it were that easy, but chemistry is never that easy. So it's the first orbital. It matches the rows for S and P orbitals, but once we get to D orbitals, the rows don't match up with the numbers. But that's for another problem. But then what we want to do is find our next set. So then we go to 2s, and 2s entails lithium and beryllium. Since we're still not to this carbon molecule, we will then write 2s2. And then we want to get to the carbon, so we have 2 more elements before the carbon. So we would write 2p. It's the second p orbital, so it's really the first p orbital, but every orbital kind of shifts. S starts at the value 1, P starts at the value 2, D starts at the value 3, and F starts at the value 4. Not confusing at all. It actually is very confusing. I don't know why it doesn't match up with the rows, but Anyways, that's what P always starts with 2. So we have 2P. And then since we have 2 elements until we get to carbon, we put 2P2. So that is our electron configuration for carbon. Thumbs up if you're understanding. I know this is a little bit tricky and it's kind of hard to grasp conceptually at first, but I'm hoping we get lots of practice tonight. Again, if you're just now joining and you have any questions, please type those in the chat. I want to help you with whatever you guys need help with. So I encourage you ask as many questions as you can, and I will answer all of them that I can. All right, now let's move on to another electron configuration. This time is calcium, so Ca. Calcium is on the periodic table right here. It's kind of difficult to find like elements on the periodic table when you're first starting out with chemistry, but I promise with practice, you'll be able to point right to them. So we want to find the electron configuration of calcium. So let's label where all of our orbitals are again. And for this problem, if you've already kind of started talking about electron configurations in your classes, or you kind of already know them, try to beat me to solving this. I'm going to go kind of slow so that we all understand, but I encourage you to try to beat me in solving this. From EXO on TikTok, I am covering S&P orbitals with this electron configuration. SP orbitals are entailed in this. We'll kind of touch on that. So keep following along. But we start with labeling this as S, this is P, this is D, and this as F. So hopefully everyone remembered that from the last time. And then we want to do the long configuration to start. We haven't touched on short configuration yet, but we will. We start with 1 and 2 S. So we have our 1 S's, which is hydrogen and helium, because S has 1 orbital of 2 electrons. So the 1S has 2 electrons. All S orbitals have 2 electrons. Get that in your head. S has 2, P has 6, D has 10, F has 14. Also, based on how we label, you can tell that by how many different columns those S, P, D, and F labels entail. So we have 1s2 because that hydrogen and helium are both present before we get to calcium. Then we go to lithium and beryllium. So we have 2s2. That's our 2s category. And then we have boron, carbon, nitrogen, oxygen, fluorine, and neon. That is our 2p6. So 6 because there's 6 elements, 6 electrons. Also, another way you can count by atomic number. We'll do a little check and I'll show you more about that. But atomic number, so 5, 6, 7, 8, is also how many electrons are present in that neutral element. So then we're going to go to sodium and magnesium, which is our 3s2, because we're now to that third row of S. And there are 2 electrons. And then we have aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So that is 3p6 because there are 6 elements, 6 electrons covered, potassium and calcium. So our 4s2. So in this, we have multiple S and P orbitals. Sometimes those S and P orbitals group together in sp orbitals, and they can have like a different number. And those are very important in organic chemistry. I'm not going to go too in depth to sp orbitals. We just know they are present in this calcium because we have S and P. But at the end of this, we're going to show you a QR code with all of the help session hours. And there is a specific help session for organic chemistry, which I'm sure they go in super depth of sp orbitals. So I'll point that out at the end, but I encourage you to scan that QR code to find the organic chemistry live office hour, and they'll probably be able to help answer your question more in depth. But then what we want is the short electron configuration of calcium. Now, the way that we do this, actually, I'm getting ahead of myself. I told you guys I was going to go over how the atomic numbers match up with this. My bad. So now you're wondering, how what does this even mean? How do I check myself? What am I doing? This is how you check yourself. You want your number of electrons you've added to equal your atomic number. So the atomic number of calcium we see is 20. It's very tiny, but I'll blow it up so y'all can believe me that the atomic number is 20. And we want to count the number of electrons. So we had 2 electrons that we said here. All of those subscripts are the number of electrons. So we had 2 plus 2 plus 6 plus 2 plus 6 plus 2. Now, if you have your calculator out, put that all in your calculator and let me know what you get. You should get, though, 20 because your number of electrons should equal your atomic number. So if you got 20, you know you found the electron configuration correctly. So great job, guys. Now I'm going to show how to find the short configuration. So these configurations can get extremely long, especially if you're doing like whatever MD stands for. I don't know. I'm not sure. It looks like something I can't pronounce. But if you're finding the electron configuration of MD, it is going to be a lot of writing. It would probably be multiple lines of electron configuration, and that's just not practical for chemistry or for chemists. So we've developed what we call the short electron configuration system. Most of your teachers will require you to learn it and probably require you to write it this way the majority of the time. I know mine did. But basically what we do is we go to our last noble gas in our periodic table, the last one we hit before we got to our element. So if you're wondering, hey, what is a noble gas? Noble gases are this last column of the periodic table, and they have a perfect octet of electrons. They have 8 electrons. And so what we do is to mark our place in the periodic table, we put the last noble gas that we hit in brackets. So before calcium, the last noble gas is argon right here. So we would put argon in brackets, and then we just write the electron configuration that's remaining after that. So if we write argon and then we have potassium and calcium, all we have to do is Ar4s2. And any chemist, any scientist can read this and be like, oh, okay, they're talking about calcium. That is this short electron configuration for argon. If you're understanding, send a thumbs up in the group chat, or not the group chat, the chat for the video. Send a thumbs up on TikTok or YouTube to make sure that everyone is getting it. We are going to do one last little step with this problem. Some teachers, mine did, require spin configurations, which is really, I think it's fun once you get the hang of it. So I do want to teach it, especially if it's going to be on your test. But basically, it is a way to show orbitals, subshells, and spins. There's different rules. I'm not going to say the rules by name, but as we go through this, I'm going to show you. I'm going to talk through it. Just watch for this first one, and then we're going to do another one. So I encourage you for that one to try it for yourself. But I would start by directly matching them up to my long configuration. So let me change colors so that we can better see this. So I have a 1s2 right here. S has only one subshell, but each subshell has 2 electrons. So S has 2 electrons, 1 subshell. The subshell is represented by this line. So the S would have 2 arrows, each in opposite spins. A rule of these spin configurations are that each electron has an opposite spin. So we have an up arrow and a down arrow. And that represents 1s2. Then we want to go to 2s. So I have 2 electrons again for the 2s2. And so that is also going to get an up and down spin. They can never have the same spin in the same subshell. So again, s orbitals. 1 subshell represented by that one line at the bottom, 2 electrons represented by the up and down spins. Then we get to our 2p6. Now, p orbitals have 3 subshells and 6 electrons. So we represent the 3 subshells by 3 lines. We do our up arrows first. We have 1 electron, 2 electrons, 3 electrons. Then we go to down. 4 electrons, 5 electrons. If there were only 5 electrons in this p orbital, we would stop right here. But then since we have 6, we're going to add another down arrow. If this isn't making sense, if we need to go over it slower, just let me know. And if you have any questions, we are now about 2/3 of the way through our live stream. So I encourage you, ask any questions you have in these last few minutes that we have. I want to help you better understand chemistry, so please ask those questions. Next is 3s2. So we have our 3s orbital, 1 subshell, 2 electrons. So up arrow, down arrow. Then we have 3p6. So 3p, 3 subshells, 6 electrons. Up arrow, up arrow, up arrow, down arrow, down arrow, down arrow. And then last but not least, our 4s2, which is right here. Wrote that in the wrong place. My bad, guys. 4s, and there's 2 up arrow, down arrow. So that in green right here is the spin configuration of calcium. Hopefully we're all understanding. If we're not understanding, let me know in that chat, and I would love to help you. Now let's move on to another electron configurations problem. I want to challenge you guys to attempt this one on your own first. I wrote these out of order. We're actually going to start with the long, but we want to find the electron configuration of rubidium. First, I want to do kind of a challenge. Does anyone know the chemical symbol for rubidium? You have about 15 to 20 seconds. Tell me, what is the chemical symbol for rubidium? Get a virtual high five if you know. I'll be very, very impressed. This is a challenging one. All right, about 10 more seconds, guys. What is that chemical symbol? Is it, I'll give y'all some options. Is it RH? Is it RF? RU? RG? RN? Does anyone know? 5, 4, 3, 2, 1. If you said RU, you are absolutely correct. And we find RU right here on the periodic table. Oh, wait. No, Jubaba on TikTok, you're actually correct. I think you might have, yeah. RB is correct. Y'all are catching me tonight. I don't know what I thought RU was. Let's learn. What is RU? RU is ruthenium. Okay, well, you learn something new every night. Y'all are teaching me something. And yeah, RB is absolutely correct. Y'all caught me. See, this is why y'all have to engage so that y'all can try to catch me and get the answer correct before me, or get the correct answer when I don't. But RB is absolutely what we're trying to look for. RB is right here. So I'm going to start you out with labeling the periodic table for you. So we have our s orbitals here, p right here, d right here, and f right here. All right, tell me, what is the long configuration of rubidium? You've got about 1 minute, and I'm going to start writing then, but I encourage you, beat me to this or get it right when I don't. But I think I've got this one for you guys. So tell me, what's that long configuration? All right, about 30 seconds, and I'm going to start writing if any of us are struggling. About 20 seconds. See if you can beat me to solving it. And if you have any questions, type those in the chat. I'd be more than happy to answer them for you. Any homework questions, questions you went over in class, or just conceptual questions, I would love to help. All right, so this is where I would start. I have hydrogen and helium, 1 s orbital and 2 electrons because both are present. Lithium and beryllium, 2 s orbital, 2 electrons, both are present. boron, carbon, nitrogen, oxygen, fluorine, and neon, 2p6 orbital. All 6 atoms and electrons are present. Sodium and magnesium, 3s2 orbital. Aluminum, silicon, phosphorus, sulfur, chlorine, argon is 3p6. Potassium and calcium is 4s2. Now, this is where it gets kind of tricky. We haven't touched on this yet. Well, I kind of touched on it earlier. D starts with 3, starts with the number 3. I don't know why. Some teachers will put the 3 with the 3s and 3p. I find it easier to just go left to right down the periodic table. So all of these 3, 4, 5, 6, 7, 8, 9, 10 are included before I get to rubidium. So it's 3d10. And then we have 1, 2, 3, 4, 5, 6. If y'all didn't know, krypton's actually on the periodic table. That's what Kr is right here. It's pretty cool. And then 4p6. And then we get to rubidium, which is our 5th s orbital. And that is just 5s1. All right, that was a super long electron configuration. Thumbs up if we got that. I'm going to give y'all 10 seconds. Thumbs up if you got that. Are we following along? Are we understanding how to find those short and long configurations? If you need more help or you're not understanding, put a thumbs down on the TikTok, YouTube chat, whatever it is, just so I can kind of gauge where everyone is. All right, about 4 more seconds. Thumbs up or thumbs down, guys. Alrighty, I'm not seeing any thumbs down, so we're going to continue. We're going to go to that short electron configuration. So you've got about 30 seconds. Tell me what that short electron configuration is for rubidium. What would it be? All right, about 15 more seconds. So from Jubaba on TikTok, I'm seeing KR5S1, and you are absolutely correct. Great job. I'm glad we're getting the hang of it. If anyone is having any more questions on electron configurations or any trouble, let me know. Good job from Maylee on TikTok. Krypton with the 5s1 after is absolutely correct. And now we're going to move on to the spin orbitals. So let's work on those. This one's hard to type in the chat, but if you want to tell me any of the rules for it as I go along, definitely let me know what you would do, how you would solve this. What I would do is start with our 1s. And so I have 2 electrons present there. I'm going to, again, change my color so that we can all kind of see what's going on. I have 2 electrons there, so I start with an up spin and then a down spin. And that's 1s. Then got my 2s. I have 2 electrons, up spin, down spin. All right, guys, next I'm at my 2p6. How many lines am I drawing? You've got 20 seconds. How many lines, so how many subshells should I draw for my p orbitals? How many lines or subshells should I draw for my p orbital? All right, about 5, 4, 3, 2, 1. So I have 3 lines. I'm going to go, and I have 6 electrons. So if you said 3 subshells, great job. 3 subshells equals 3 lines. Up, 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 down, 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 because I have 6 electrons. Then we're going to go to 3s. I have 2 electrons, up, down. 3p6. Okay, I'm going to give y'all a second chance. How many subshells or lines should I draw for this one? All right, about 10 more seconds. 5, 4, 3, 2, 1. All right, you should have said 3. It was on the board. So 3p, we have 6 electrons. Up, down. Well, I should do ups first, but since it's full, up, down, up, down, up, down. For S2, we have 4s. So we do an up and then a down because there's 2. All right, here's another challenge problem. How many lines am I going to draw for this 3D10? So at least 2. I'll stop. So this time you'll actually have to kind of guess. All right, about 5 more seconds. 3, 2, 1. So if you said 5 lines, you're absolutely correct. Then I would write 10 electrons in. So up, 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 down, 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 down. And then we'll start a new one down here. P, we have 3 orbitals because of 3 subshells. We go up, then up, then up, and then we go down, then down, then down. And then last but not least, we have 5s. Since there's only 1 electron, how do we represent that, guys? Let me know. You've got 20 seconds. How do we represent that 1 electron? How do we represent that 1 electron? Let me know. All right, if you said just 1 up spin, you're absolutely correct. Great job. So that is our spin configuration for rubidium. All right, so from Maylee on TikTok, we have, is there any way you could cover the molecular orbital theory? I'm going to try my best. I can cover it, but what I am going to encourage you to do after this is at the end of this, there's going to be a QR code in the top left. Scan that QR code because there's an organic chemistry session that meets every week. And they do this stuff all the time, I think. So the molecular orbital theory, they will be talking about a lot. And you could ask them any question you have about this. I'm going to do a fairly basic one that will still probably apply to basic chemistry. But it's if we have 2p and 2p orbitals going together and they're side by side, we want to figure how are those orbitals overlapping. So the way I would draw this is I would kind of do a little diamond shape. And our furthest diamonds are going to be our S's, and our inner diamonds is going to be our P's. And basically what we have is we count how many subshells are in P. We kind of went over this. There's 3 subshells, so 3 lines. That's how many overlapping orbitals we're going to need for the molecular orbital theory. Basically, we start with an S, so we could do a 2. We would do an S orbital, which S is always a sigma bond. So we have a sigma orbital to represent one of these. So we could cross out 1. So we'd have 1 sigma on each. Oops, that was a bad sigma. And then we're going to have 2 pi's. So 2 pi bonds to represent our other lines on each. And they're also labeled 2 p's. So we'd have, this should be an S. We should have 1 2s orbital and then 2 p's to represent that bond. So there's a 2s sigma bond and 2 pi bonds, which are 2 p's. If you just had S's, there would just be sigma bonds. So S equals a sigma bond, and then P's equal a pi bond. That's a very brief overview. I know that's not a ton of detail, but again, I'd encourage you to look on Cheg's website for when those organic chemistry office hours are going to be, and they'll be able to go over this in much more depth. This is a little bit more advanced for this part of the course, but I think this part will apply to everyone. So hopefully you learned something new with this. We are going to answer one last question from Jellybean53 on TikTok, and that is, what are rate laws? And what about rate laws? So I'm going to give a little brief overview. Basically, rate laws, we have first order, zero order, and second order, and they tell us how fast a reaction occurs. The zero order is a slow reaction. It's linear. First order is a faster reaction. It is more of like an exponential. And then second order is a super fast reaction. So we have three different types. For zero orders, we're going to have our rate is equal to K, which is equal to something, the concentration of the zero power. That's a zero order rate law. And then we go for first orders, we have rate equals K. We always have K, it's our rate constant. K equals something to the first order. And then for second order, we have our rate equals K, which is our rate constant, equals, it could be a concentration times another concentration. So we could have X times Y, or we could have K equals X squared, or K equals Y squared. All of these are examples of second order rate laws. And so they change with time. Every rate law equation has different like half-life equations that go with it, and different ways to find things. We have some ICE tables that we do where we determine like the K value and how quickly those concentrations are changing at equilibrium. Oh, words are crazy. But basically, this order can keep going up as exponents come up. So you could go to fifth order and have like rate equals K equals X to the second, Y to the third, or any combination of that. That's how we get that order of the rate laws. And then let's see, we have some different types of ways that we can write them too. I'll do more with this next week. It's a big concept to go over mathematically right now, but conceptually we can kind of try to understand it. For zero order reactions, we basically have two types of ways to figure out what that rate constant is. We have differential rate laws, which would be like the negative dA, the concentration of A over dt equals K. We have integrated rate laws. This is the one I see the most people use. So we'd have A equals A sub O minus KT. And then we could find our slopes. So each of the different orders has a different way to find slope. It's negative K. You're probably like, okay, why are you writing all these random equations on my screen? The reason is if we want to figure out anything about the rate, if we want to figure out our K value, which is our reaction constant, the time it took to reach equilibrium, which is T right here, our initial concentration, which is A sub 0, or just our concentration at any time T, which is that A, we have to know these rate laws. We have to know these slopes and these differential rate laws. I will say integrated rate laws are seen the most. And then also another important thing is zero order, first order, second order. They all have different units. So zero order, which I had to memorize these, so I don't know if y'all will have to memorize them, but it might be something good to ask your teacher or start working on, is moles over liters over seconds. That's our units for zero order rate laws. And that will be the unit for your K, which is your rate constant. And then for first order rate laws, we have a unit of 1 over seconds. For second, we have liters over moles over second. And you can find that by solving the equations. Basically, that's a brief, very brief overview of rate laws, but I encourage you to come back next week and I will do some more math with these and explaining how to do the math. That wraps up our session for today. It was so great to have all of you all. Thank you for joining the Chegg Stoichiometry live office hours. I encourage you to look at our website and the social media for other office hours that we're going to be having throughout the week. I know there's organic chemistry to all of you all who had specific organic chemistry questions. There's regular chemistry who might go into depth more about the conceptual side of rate laws. Next week, I will definitely have some rate law questions for us so that we can kind of understand all this conceptual math that we just went through. But it is so great to have you. Thank you all for joining, and I hope you come again next week. And thank you to Chegg for putting these live office hours together. I will